Okay, there we are. All right. Good afternoon, lads and ladies. Welcome back to Calc 2. Today we are going to talk about partial fractions, which is section 7.4 in the textbook. And as a sort of lead up to that, I want to ask you a few kind of basic algebra questions that turn out to have deep answers. So let me get this screen share rolling. Here, all right. This is MAC2312, section 004. It's a lecture. And today is the 4th. All right. So, like I said, today we're going to talk about partial fractions. The full term for this procedure that we're going to learn today is partial fraction decomposition. You will see me abbreviate this as PFD because I don't want to write that whole thing all the time. And this is section 7.4 in the textbook, which is the last section of new material before we're ready for exam 1. Section 7.5 I will talk about next week, but it's not introducing anything new. Section 7.5 is just a mixture of old problems and a little discussion of, which method to use when. It's an important section. You should read it. But it's not introducing a new skill. So let's get to it. I have a question. If 7x squared minus 3x plus 4 is equal to ax squared plus bx plus c, can you tell me what a, b, and c have to be?
Seven, -3, and 4.
Yeah. It's not immediately obvious that this is true, right? It's not immediately obvious that the only way for these functions to be identical is if these constants line up. But it turns out to actually be a two-way implication. It's an if and only if. If you plug in x equals 0, then the first two terms from the left will drop out, and the first two terms from the right will drop out, and you get 4 equals c. And then you can plug in any two other numbers you want for x, and you'll get a system of linear equations that you can solve for a and b. In general, so this is true in general, that if two polynomials are equal, are identical, which is meaning always equal or equal for all values of x, then the coefficients of each power of x must match on both sides. This is a fact of linear algebra. We say that the set, 1x, x squared, x cubed, x blah, 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 up to x to the n, is a linearly independent set in the vector space of all polynomials degree at most n. That's a fancy way of saying precisely what's on the page here. This is going to turn out to be really important for partial fractions. This, it turns out, is sort of the underlying thing that makes PFD work. So what is PFD? Let's tuck this in our pocket and move on. PFD is an algebra process. No calculus involved. PFD, shit, this pen is smudgy, is an algebra process for undoing the procedure of having a common denominator and adding rational functions. So it's not a calculus thing. It's a purely algebra thing. And what it does is it takes a complicated rational function and it lets you split it up into a sum of simpler rational functions. Let me show you what I mean. If you want to add these two guys, how do you do that?
You need common denominators. So you multiply the first one by x minus 1 over x minus 1, and the second one by x over x.
Good. Right? If I want to add these two, I need to rewrite them with the same denominator. This guy has a factor of x downstairs, but no factor of x minus 1. This guy has a factor of x minus 1 downstairs, but no factor of x. So I multiply the first guy by x minus 1 over x minus 1. That will introduce an x minus 1 factor downstairs without changing his value. This is still equal to 1 over x. The second guy, in order to get him the factor of x he was missing downstairs, I multiply by x over x, but this is all still equal to this. So this is x minus 1 over x times x minus 1 plus x over x times x minus 1, which is going to give me x minus 1 plus x over x times x minus 1, which is 2x minus 1 over x times x minus 1. Everybody agreed? Okay.
I agree. Just let me get like a couple seconds to write all that down.
Sure. Partial fractions asks the question, if I gave you this, could you go back to this? If I gave you this, is there an easy way, or indeed any way, to go from here back to here? So I'll call this expression 1. I'll call this expression 2. We know they're equal, right? These are definitely equal to each other. So partial fractions asks and answers the question, given the expression 2, which is 2x minus 1 over x times x minus 1, can we go back to the expression 1, which was 1 over x plus 1 over x minus 1. Question mark. And you might ask, why would anybody ever want to do that? Fair enough. Well, what if I wanted to integrate this? At a glance, I have no idea how to integrate this. Maybe U sub would work, maybe not. Maybe something else would work, maybe not.
Well, here, if we have 2x and x squared, if you bring the x into the bottom denominator, so we have the derivative of the bottom and the top.
It's true that the particular example here that I just made up happens to work with U sub, but in general, if I wanted to integrate something like this, I'm not always going to be able to do it with U sub. Most of the time I can't. So the question is, how do you go, if you want to do an integral of a function like this in general, how do you do that? And the answer is you run PFD to rewrite it as some shit like this, because this shit I know how to integrate. No matter what the linear factors are downstairs, no matter what the constants are upstairs, I know how to integrate 1 over x. I know how to integrate 1 over x minus 1. I know how to integrate anything that looks like that. But in general, I don't know how to integrate anything that looks like this. So let me walk you through a very simple example to kind of show you what this procedure looks like. And then we're going to slowly ramp up, and I'll describe the general strategy at the end, because the general strategy here is pretty frightening. It just looks scary if you write it all down at once. It's not scary to do it, but it looks scary if you write it all down at once. All right. So I want to do the integral . 1 over x times x plus 1 dx. Here, U sub won't help me, right? You can distribute your x down here, you get x squared plus x, but there is no 2x upstairs that I can work with. There is no derivative of the bottom hanging out at the top. So what I do is I step aside. I put the integral away for a minute, and I say, I want to do some partial fraction decomposition. I want to know, can I write 1 over x times x plus 1 as some constant over x plus some other constant over x plus 1? It turns out that we always can do that. And our task is to just try and find the constants a and b. Now, if these things are equal, then I can multiply on both sides by x times x plus 1. On the left-hand side, everything cancels. And on the right-hand side, I have to distribute. Here, the x's will cancel, and I'll be left with a times x plus 1. Over here, the x plus 1s will cancel, and I'll be left with b times x. And now here's where that polynomial shit from the start is going to become important. This is ax plus a plus bx, which is a plus b times x plus a. Just distributing the a over this term gives me these. And then I put like terms together. Ax plus bx is a plus b times x. Factor out the a plus b, factor out the x. And a is just a. And this is still 1. This is still 1. And I'm going to think of this as 0x plus 1. So a plus b has to equal 0. And a on its own has to equal 1. We are equating coefficients, just like we did in the very first thing, right, with the quadratic. So this implies, or is actually equivalent to, the system. Now, thankfully, this is a really silly 2x2 system. This is not a hard system to solve. A plus b equals 0 and a equals 1. Those are my two linear equations. Since a equals 1 by equation 2, we know that 1 plus b equals 0. So b has to be -1. Therefore, 1 over x times x plus 1 is equal to a over x, which is 1 over x, plus b over x plus 1, which is -1 over x plus 1. Therefore, the integral of 1 over x times x plus 1 dx is equal to the integral of this. Integral of 1 over x minus the integral minus 1 over x plus 1. And now we split up the integral and handle each one however you want, right? Whatever tools you got. So that's integral 1 over x dx minus integral 1 over x plus 1 dx. First guy is a straight up natural log. Second one's a little u sub. I'm making the substitution in the second integral only. That's why I split them up. And you get integral 1 over x dx minus integral 1 over z dz. Which is the natural log of the absolute value of x minus the natural log of the absolute value of z plus a constant, which is the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 plus a constant. And that's your answer. The integral wasn't hard, but the algebra was a little sneaky. In fact, the algebra here was profoundly sneaky. Who the fuck told me that I could even do this? Right? What? Why? How? Who knows? That's a question that you need some linear algebra to answer. we're not really prepared to answer that question, but I'm going to do my best today to give you a version of an answer that you can stomach, because we're not ready for that yet because we don't know anything about spanning sets and vector spaces, but I'm pretty sure I can convince you. And then the other big thing is, like, what are the mechanics of this process like? You know, how did we get A and B? Can we always find A and B? And under what conditions can we set up a thing like this? So those are the questions I aim to answer today. All of the integrals in today's lecture are going to be utterly trivial, right? When it comes to the actual antiderivative step, there's nothing complicated, I promise. But the algebra is a little bit interesting.
Okay, I'm trying to wrap my head around this, but how did you derive that a plus b equals 0 and a equals 1?
So remember the little quadratic thing we did at the front?
Mm-hmm.
So I had a 7 on the left attached to x squared and an a on the right attached to x squared, so a had to be 7. Well, I had a 0 attached to x on the left and an a plus b attached to x on the right, so a plus b had to be equal to 0.
I suppose so. It'll
It's the
take a
same
little
thing.
bit.
Yeah, it's really the same thing. The coefficient of x on the left has to be the same as the coefficient of x on the right. Coefficient of x on the left is 0. Coefficient of x on the right is a plus b. And then in the same way that c had to be 4, because the constant on the left is 4 and the constant on the right is c, 1 has to be equal to a, because the constant on the left is 1 and the constant on the right is a. This
All right.
is a surprisingly powerful tool. Right? The fact
Oh,
that
I
you
see.
have two polynomials equal to each other, you can set the coefficients of each term equal to each other.
Okay, so you're just visualizing this like a little linear equation, and it's a little sneaky, but it works out.
It does.
I'll trust you.
Yep. Yeah, it's certainly very sneaky, but it does work.
Okay, I appreciate it.
Of course. Yeah, this
So
is
if on the right side, we had a term of x squared, we would put on the left side 0x squared.
Yep.
All right.
Will there
So
ever be any anything that'll let us know when we should use this, or will we just kind of know?
that's what I'm going to kind of lead into next. So let's talk about that. What is a rational function? It's a ratio of two polynomials. And remember, a polynomial is any linear combination of positive powers of x and constants, right? So you got to be careful with your definition of polynomial also, right? No fractional powers, nothing like that. But a rational function is any ratio of polynomials, so R P over Q, where...
So would an integer be a rational function?
Yeah. Silly examples, yeah, for sure. F of x equals any constant is a rational function. Right, C over 1. Here's your P of x, here's your Q of x. kind of silly. The degree of P is 0. The degree of Q is also 0. Kind of a boring example, but it's an example. Any polynomial is a rational function. The way to think about it, guys, polynomials are the function version of whole numbers. Rational functions are the function version of rational numbers. So here, this is, I think of this as x cubed minus 7x squared plus 3x minus 5 over 1. P of x is the numerator. The degree of P of x is 3. Q of x is the denominator. The degree of Q, the degree of a constant function, is 0. And then the more obvious examples are the more obvious examples. Right, like this is also a rational function. P of x here is x plus 2. The degree of P of x here is 1. Q of x, the denominator, x squared plus 7x minus 5. The degree of Q is 2. I'm writing out the degrees here for a reason, because I'm going to define a special subclass of rational functions called proper rational functions. I'll call a rational function proper if the degree of the bottom is bigger than the degree of the top, strictly bigger. A rational function, R of x equals P of x over Q of x, is called proper. So a proper rational function, provided the degree of Q is strictly bigger than the degree of P. Partial fractions is a tool we use when we want to integrate a proper rational function for whom nothing else works, like u sub doesn't work. So we use PFD when integrating proper rational functions for whom other methods don't work. Really, the only other method you could hope to use here is u sub. No reason to ever jump in with integration by parts on a thing like this. Sometimes, like 1 over x squared plus 1, you can do with trig sub, and you should. It's fast. Like you can't use PFD on that. So if you're looking at a proper rational function, and none of the other stuff we've talked about so far is going to do the job, then you'll use PFD. And this is surprisingly common. A lot of stuff we handle this way. Most rational functions.
What if the bottom can't be factored?
It's a fun question. We'll get there. But it's a fact that every polynomial can be factored. It depends on the framework you're willing to exist in. If you're willing to work with complex numbers, then any polynomial with integer coefficients can be factored into linear terms. If you're not willing to work with complex numbers, if you insist on working just with real numbers, then every polynomial can be factored into a combination of linear terms and irreducible quadratic terms. So there's no such thing as an irreducible cubic polynomial. There's no such thing as an irreducible fourth degree polynomial. You can always break them down into linear terms and irreducible quadratics. There are irreducible quadratics like x squared plus 1. And we'll see how to handle those. There's a regime for handling those. And we're getting close. Okay, we're getting close. So let me grab an example here. These ramp up pretty quick, so I want to take my time getting there. Let's do x plus 5 over x squared plus x minus 2. Why not? What was it, minus 2? Yeah. All right. The book does this in a kind of funny way where they treat this the way I treated our first little toy example here, but I want to do this with PFD. This is a proper rational function, right? The degree of the bottom is 2, the degree of the top is 1, so the degree of the bottom is strictly bigger. If that wasn't the case, can't do PFD. PFD only applies to proper rational functions. I'll show you how to handle improper rational functions. You just do long division, right? Polynomial long division. We want to run some partial fractions on this bad boy, which means I need to start by factoring the bottom. So how does this bottom factor? This is going to be x plus 2 times x minus 1. So my setup here is going to be x plus 5 over x plus 2 times x minus 1 equals, I get one term for each of these simple linear factors. I ask, where could this have come from? What sort of shit could I have added up to get something looking like this? And the answer is, could have come from something like a constant over x plus 2 plus some other constant over x minus 1. The fact that I require the rational function to be proper at every stage of the procedure tells me that I'm allowed to just say it's a constant up here, not like bx. So anything like this, proper rational function with 2 distinct linear factors downstairs, can always be broken down as a constant over the one linear factor plus another constant over the second linear factor. Anything like this has to come from stuff like this. Or if you put together any combination of stuff like this, you will always get something like this. This is what I call the PFD setup. The PFD setup is all important in these problems, and unfortunately, it's not always this nice. There are some pathological cases like irreducible quadratic factors that Alexander was asking about, or repeated linear factors like x minus 1 quantity squared. I'll show you how to handle those, but for now, this is the correct PFD setup for a proper rational function like this. Our next step is to multiply by x plus 2 times x minus 1 to clear the denominators. Last time I wrote that out really carefully. This time I'm just going to write down what you get. If you multiply by x plus 2 times x minus 1 on the left, they'll cancel and you'll just get x plus 5. If I multiply a over x plus 2 by x plus 2 times x minus 1, then the x plus 2's will cancel, and I'll get a times x minus 1. If I multiply b over x minus 1 by x plus 2 times x minus 1, then the x minus 1's will cancel, and I'll get b times x plus 2. Now I'm going to distribute out all the terms on the right. And combine powers of x, combine like terms. So I have ax here plus bx there. So I'll have a plus bx. And then my constant term is going to be negative a plus 2b. And all this is equal to x plus 5. Now I can set the coefficients on each side equal to one another. The coefficient of x on the left is a plus b. The coefficient of x on the right is 1. We don't normally write it, but x is 1x. This is something we're all familiar with, right? The constant term on the right is negative a plus 2b, and the constant term on the left is positive 5. So a plus b has to be equal to 1. And negative a plus 2b has to be equal to 5. Which is a 2x2 system of linear equations that I can solve for the constants a and b. I'll pause here for a minute. In the future, I'll give you a shortcut. There's a shortcut we can implement at this stage that would work to find a and b quite quickly here, but it doesn't always work. So it's important that you learn this method first. Questions on how we got to that linear system? Okay, who knows how to solve this linear system? What's the fastest way to solve a linear system like this?
Add them up.
Yeah, add 'em, elimination. So if I add row 1 to row 2, a plus negative a is 0a, and b plus 2b is 3b. 1 plus 5 is 6, which tells me b has to be 6/3, which is 2. And then we back substitute. So now equation 1, a plus b equals 1 becomes a plus 2 equals 1, which means a has to be 1 minus 2, which is negative 1. So x plus 5 over x plus 2 times x minus 1 is equal to negative 1 over x plus 2 plus 2 over x minus 1, which means the integral of x plus 5 over x plus 2 times x minus 1 dx is equal to negative integral dx over x plus 2 times the integral dx over x minus 1. All right, just integrating on both sides. I popped out the constants, split up the integrals in a single step there. In the first integral, I'll make a substitution for the bottom. In the second integral, I'll make a substitution for the bottom. So in the first guy, I'll let z be x plus 2, dz is dx. In the second guy, I'll let w be x minus 1, dw is dx. So this will become negative integral 1 over z, or just dz over z, plus 2 integral dw over w. And then just to save the paper here, this is negative ln abs z plus 2 ln abs w plus c, which is negative ln x plus 2 plus 2 ln x minus 1.
Can we leave it there, or would you want us to move the exponents in and multiply them together?
I'd leave it. I'd just leave it like this. This is fine. You can combine the logs after bringing the constants in as powers if you want to, but for my money, it's not worth it, not worth the time. Just leave it like this. So the miracle is getting to this step, right? The miracle is somehow undoing that common denominator, even though I don't know what was up here. So being able to undo this guy into two simple rational functions based on the shape of the denominator. That's the game. Hopefully you're starting to feel comfy with this. I'm going to do one more example here where I show you a trick, and then I'm going to show you how these things can get shitty, because they can get shitty. Questions on this?
When we have like a simple linear function like on the bottom, is it always going to be like ln of over that like simple linear?
Kind of. I recommend actually making the substitutions here. If there's a number in front of x, like 2x plus 5 or 3x minus 1, then you're going to get a constant factor out from the differential. So this is a fun enough question that I want to answer it well. Under what conditions, totally unrelated, just think along with me, nothing to do with PFD. Under what conditions is the integral of 1 over f of x dx equal to the natural log of f plus c? The answer, only if f of x is equal to x plus k for some real number k. Right? So yeah, if you have like 1 over x plus 3 or 1 over x minus 2, those will always come out to natural logs of the bottom. But if you have 1 over 2x plus 3 or 1 over 5x minus 2, even those don't come out like this. In general, I'll say this real clearly because this is a question I like to put on tests. In general, this is a false statement. This is only true if f is a linear function with slope 1. Anything else doesn't work.
Well, wait a minute, hold on here. So I was taught in Calc 1 class back in my high school that if it was like 5x plus 4, it would be ln of absolute value of 5x plus 4, and if there was nothing at the top, you would just put a 1/5 out in front. Is that not true?
Well, no, the 1/5, yeah, exactly. The 1/5
Yeah.
changes things, yeah. So if you had 1 over 5x plus 4 that you wanted to integrate, you make the substitution z equals 5x plus 4, dz is 5 dx. So this becomes integral 1 over z times, well, what is dx? Dx is 1/5 dz. So you get 1/5 integral 1 over z dz, which is 1/5 log z, which is 1/5 ln whatever, 5x plus 4.
Yeah. So wait, you're not saying that that's not possible. You're just saying that as a neutral ln, the slope can only be 1.
Right. I'm saying
Oh,
that
okay.
if you want to use this formula, I'm saying don't use this formula. I'm saying this is not a true statement. I'm saying this only works for linear functions with slope 1. For anything else, whether it's a linear function with a different slope or a nonlinear function downstairs, you're going to have something other than the natural log of the denominator. You're going to get something a little more complicated. If you have a linear function with slope m, then you would get 1 over m times the natural log of f. If you have something like x squared plus 1, then you're going to get arctan. If you have something like 1 over e to the x, then you're going to get negative e to the negative x. So in general, 1 over f of x does not integrate to the natural log, only for these sort of functions. If you want to generalize more, you can say that you will get a natural log for any linear function f, but there's also going to be this constant multiple. So yeah, my advice is don't lean on this. The only thing that integrates to natural log is 1 over x. And if you want to know if you're going to get a natural log, do the substitution. Don't be lazy. No room for lazy. There's room for some kinds of laziness in mathematics. Mathematicians are willing to work very hard now to be lazy later. But when it comes to doing a calculation, just do it. All right, back to partial fractions. A faster way to find A and B in some PFD problems. This is called the heavy side. AKA cover up trick. If you look in the modules for our class on Canvas, you'll see I actually have linked to a paper there that discusses the heavy side cover up trick, talks about why it works, shows you a bunch of examples. I'll just do 1 or 2 here. I'll just do 1 for now, really. If I want to do this integral, I would set up some PFD. So I factor first, and then I say, okay, 1 over x minus 1 times x plus 1. I can set this up as a over x minus 1 plus b over x plus 1. And then that's the same as saying 1 equals a times x plus 1 plus b times x minus 1. This expression is supposed to be true for all values of x. So let's send x to 1. As x goes to 1, I'll call this expression star. As x goes to 1, star becomes 1 equals a times 2 plus b times 0, which is the same as just saying 1 equals 2a, which means a has to be 1/2. And as x goes to -1, the expression star becomes, well, let's see, as x goes towards -1, this is going to go to -2, this is going to go to 0. So I would get 1 equals a times 0 plus b times -2, or 1 equals -2b, which means b is -1/2. So this is a nice trick. It's a very nice trick. The idea is you look at this equation, right, after you clear out all your denominators, and you ask, what numbers can I plug in for x that make all but one of the terms disappear? If I can make all but one of the terms disappear, then I'll be able to read off the constant a or b or whatever associated with the term that didn't disappear. So you can use this to sneak these numbers out one at a time. The catch is it only works on really nice setups like these. So far, everything we've seen today, you could use this on. But the problems I'm going to show you next, this has limited utility for. So now that I have a and b, we can come back and do our integral, right? This integral would be equal to the integral of a over x minus 1, which is 1/2 over x minus 1 dx minus integral 1/2 over x plus 1 dx. That's just integrating each of these separately with the values for a and b plugged in. And this is going to be 1/2 integral dx over x minus 1 minus 1/2 integral dx over x plus 1. And again, a little u sub in each of these and you'll get the job done. I'm not even going to bother. The point is to show you the trick here. So in each of these PFD problems, we've been able to factor the denominator kind of all the way down until you just have simple non-repeated linear factors. What happens if you have a repeated linear factor like x minus 1 times x minus 1? Turns out it requires a little bit more love than you might think. And to make sure these examples go smoothly, I'm going to grab them from the textbook. If I'm honest, the way the textbook presents this is not ideal. But we'll come back to that shit there in just a minute. They make this look so much scarier than it is. This is fine. We can do this. All right. Let me approach this as though we know what we're doing. Oh no. Yeah, no, let's not do that. We're gonna look just at part of this. So don't write down what you see in the book here. I'm gonna peel off just a little piece of it. They make this shit look so much scarier than it needs to. Here we go. How do I do this? again, we have a proper rational function. The degree of the top is 1. The degree of the bottom is 3. Because if you multiplied all this out, this would be a quadratic. When you multiply that quadratic by this linear term here, you would get a degree 3 polynomial. So degree of top is 1, degree of bottom is 3. We're good to get started. I'm going to ask myself, where could an x minus 1 squared factor in the denominator come from? Well, certainly it's possible that I had an x minus 1, right? Just a term with an x minus 1. But it's also possible that I had a term with x minus 1 squared. And maybe I just had this. Maybe I only had a term with an x minus 1 squared and I didn't have any of these. But if you put two things together like this, the denominator would be x minus 1 squared. So we have to allow for the possibility that there was not just this term, maybe there was also a term like this. And then, of course, we have to allow for we have to ask, where did the x plus 1 come from? So the moral of the story is, if you have a higher multiplicity factor downstairs, you have to kind of build up to that in your PFD setup. And unfortunately, this fucks up the Heaviside trick a little bit.
Wouldn't you split the x minus 1 up into x minus 1 times x plus 1? Like, would you keep it as x minus 1 squared in your PFD sort of setup?
I want to make sure I'm understanding right. So these first two terms are both coming from this piece. And the idea is you have to ask, like, what sort of things could I have added up? What sort of fractions could I have combined that would have resulted in a factor of x minus 1 quantity squared in the common denominator version? If I have a common denominator between these two fractions, what's that common denominator going to be?
X plus 1. I'm honestly unsure.
Yeah, so let's step to the side for a minute here. I think this is worth doing. How do I add 1/7 and 1/49?
You multiply the 1/7 by 7/7.
Yeah, exactly. I don't need to do shit with him, right? So this is 1/7 times 7/7 plus 1/49. And that's 7/49 plus 1/49, which is 8/49. The result here, the denominator, oh my God, I've got sirens outside, I've got lawnmowers and leaf blowers. The denominator is 7 squared. And this thing came from adding up a term whose denominator was 7 with a term whose denominator was 7 squared. So if you combine terms whose denominator is this thing and this thing squared, the result will be something whose denominator is just that thing squared.
Okay.
Right? In other words, this doesn't contribute anything fresh to the total common denominator. The total common denominator is the least common multiple of all three denominators.
I see.
And we have to allow for the possibility that there was a piece like this that got added to a piece like this that gave me this factor in the denominator.
Okay.
Makes sense? Same sort of thing here, right? Same sort of thing that happens with the arithmetic here. If I ask, what sort of shit could I have added up to get 8/49? It could have been, 7/49 plus 1/49, but 7/49 is 1/7. So I could have had a denominator had a factor of 7, or I could have had a denominator had a factor of 7 squared. Same sort of thing here. Could have had a factor of x minus 1, could have had a factor of x minus 1 squared. Both are possible. Now from here, everything goes just like it did in our first 3 examples. I cross multiply to kill all the fractions. The left-hand side will be 4x. The right-hand side is going to be a little more complicated. If I multiply a over x minus 1 by x minus 1 squared times x plus 1, one of the x minus 1s will cancel, one of them will survive, and the x plus 1 will survive. So I'll have a times x minus 1 times x plus 1. If I multiply b over x minus 1 squared by x minus 1 squared times x plus 1, the x minus 1 squareds will cancel perfectly, and I'll just get b times x plus 1. And if I multiply c over x plus 1 by this denominator, the x plus 1s will cancel, and I'll just get x minus 1 squared. Now we're going to blow everything apart, combine like terms, and equate coefficients. This is a times x squared minus 1 plus b times x plus 1 plus c times x squared minus 2x plus 1. Now I'm going to do something that you guys want to get good at here. I'm going to collect the coefficient of x squared in one step without multiplying the rest of this out. This term cannot contribute any x squareds. The only x squareds are here and here. And if I distribute the a here, I would have ax squared minus a. So in the coefficient for x squared in the final result, there will be an a. There will not be a b. There will be a c, right? Because if I were to distribute this c, I would get cx squared minus 2cx plus c. So this is going to be a plus c times x squared. That's it. I found all the x squareds. Now we're going to find all the x's. There's no x's in here. There's a bx here, and there is a minus 2cx here. So the coefficient of x is b minus 2c. Now I'm going to find all the constants. There's a negative a here, there's a positive b here, and there's a positive c here. So this is going to be, my constant term is going to be negative a plus b plus c. And all this shit is equal to 4x, which I will understand as 0x squared plus 4x plus 0. I'll give you a second. If you want to take the extra space on the page to write out, like distribute everything, and write this as ax squared minus a plus bx plus b plus cx squared minus 2cx plus c, you can. There's nothing wrong with that. But being able to jump from this to this is a valuable skill. It'll save time. So I wanted to demonstrate that. I just look one term at a time. I ask, where are all my x squareds? I see, oh, there's a of them here, and there's c of them here. So I have a plus c x squared. And then I go, where are all my x's? I go, well, there's none of them here. There's b of them here. And there's minus 2c of them here. So b minus 2cx. And the same thing for the constant. There's negative 1 times a of them here. There's positive 1 times b of them here. And there's positive 1 times c of them here. So negative a plus b plus c. Is everybody with me up to this line down here? Are there any questions we'd like to ask?
I just had a question.
Yeah. Yeah, Nico?
So in the third step, so why did we multiply c times x minus 1 squared?
So
why wasn't it
every term here gets hit by this whole denominator. So this guy, he gets multiplied by x minus 1 squared times x plus 1. This guy gets multiplied by x minus 1 squared times x plus 1. I really shouldn't write the. And this guy gets multiplied by x minus 1 squared times x plus 1. It's just that when I multiply this by that, the x minus 1 will cancel, and I'll have one x minus 1 left over and the x plus 1 left over.
My bad. I was thinking something else. I thought it should have been cubed for some reason. Sorry.
Oh, okay. No, you're good. You're good. Everybody comfy with where this comes from? We just cancel everything we can. So when I multiply a over x minus 1 times x minus 1 squared times x plus 1, one of the x minus 1s cancels. So I get x minus 1 to the first, and the x plus 1 doesn't cancel, so I get x plus 1 here. When I multiply b over x minus 1 squared by x minus 1 squared times x plus 1, the x minus 1 squareds cancel, and I get x plus 1. And when I multiply this by x minus 1 squared times x plus 1, the x plus 1s cancel, and I get just the x minus 1 squared. So it's like cross multiplication. Ooh, that's bad coffee. Okay. Yeah. All right. We are ready now to write down our linear system. A plus C has to be 0. B minus 2C has to be 4. And negative A plus B plus C has to be 0. This is a 3x3 system. Notice that the size of the system is the degree of the denominator. So as the degree of the bottom goes up, the size of the linear system goes up. Solving this is a little bit more work. But what I see is if you add all three of them, something nice happens. You'll have A plus negative A, B plus B, and C plus C minus 2C. So you'd get 2B equals 0 plus 4 plus 0, which implies B equals 2. What else can we do? Is there anything else obvious here? Not really. So we got to start solving by elimination. You got to call back on those skills from your pre-calculus class. We make the pivot here 1, that's good. Then we need to kill the thing below. So I'm going to add row 1 to row 3. I'll leave row 1 alone. A plus C equals 0. B minus 2C equals 4. And now if I add this to this, I get 0A plus B plus 2C equals 0 plus 0.
Did you plug in 2 for the second equation? So 2
Yeah,
minus
so
4.
yeah, so now that I've got this last equation here, or this one really, either one, you can substitute your B in. So now using B equals 2. I guess my point was that you can solve this using conventional row operation methods, right? It's possible that maybe not everybody remembers how to do row operations. Do we want to go through solving this with row operations?
Yeah.
Yeah, okay, then I'm not going to take this shortcut here. My next move would be to kill the B down here. So the row op here that I did was new row 3 is old row 3 plus old row 1. And then my next row op would be let's see, I would take my new row 3 to be my old row 3 minus old row 2. So row 1 stays A plus C equals 0. Row 2 isn't changing, that stays B minus 2C equals 4. And now if I subtract this from this, what will I get? I'd have B minus B, so that's going to be 0. I'd have 2C minus negative 2C, that's going to be 4C. And I'd have 0 minus 4, that's negative 4. And now I've got this in what's called triangular form. You remember your matrices or system stuff from pre-calc? This row operation gets my system into a upper triangular form. So now I can read off, since 4C equals negative 4, we get that C is negative 1. And now that I have both C and B, I could, in theory, plug back in to find A. I didn't even need B to do that, but yeah, now by row 1, A plus negative 1 equals 0. So A is 1. And that's it. We found A, B, and C. You may want to remind yourself how to solve linear systems. Solving linear systems can be a bit of a pain. And I want to talk a little bit about how the Heaviside trick interacts with this sort of problem. At this line, I could try my Heaviside trick. I can send x to 1, and that will make this and this go away. So if I plug in 1 for x, I'll get 2b equals 4. So b is 2. That would get me b right away. If I send x to negative 1, this and this term will drop out. This, when x is negative 1, would be, let's see, negative 2 squared is 4, so 4c equals negative 4. So c would be negative 1. We get that. But sending x to 1 or to negative 1, both of them kill this term. So I would not be able to get A using my Heaviside or cover-up trick. So this procedure, this is the kind of official normal way to solve PFD, right? You set up the linear system and then you solve the linear system. But you ideally want to combine those methods to make everything go as nice as possible. And the truth is there are some other slick tricks out there. Let me link you to something really quick. MIT, yeah, partial fractions lecture. There we go. So I'm going to show you everything I can, but I encourage you guys to watch this lecture also. Oh, that's the Google API link. That's awful, isn't it? Here we go. This is a good video. This lecture is really nice, and this guy kind of talks about some tricks you can use to speed up the procedure. Let's go ahead and finish our integral, and then I'll let you guys take a quick break. So we found A, B, and C. So what we've discovered is that 4x over x minus 1 squared times x plus 1 is equal to A over x minus 1, that's 1 over x minus 1, plus B, which is 2 over x minus 1 squared, plus C, which is negative 1 over x plus 1. And so now, to do my integral, I just integrate on both sides, 4x over x minus 1 squared x plus 1 dx equals integral of all this shit, 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1 dx. And now you split this up. That's dx over x minus 1 plus 2 integral dx over x minus 1 squared minus integral dx over x plus 1. This guy gets the substitution w equals x minus 1, dw equals dx. This guy gets the substitution z equals x minus 1, dz is dx. And this guy gets the substitution y equals x plus 1, dy equals dx. And you end up with integral 1 over w dw plus 2 integral z to the negative 2 dz minus integral 1 over y dy, which is ln abs w minus 2 times 1 over z minus ln abs y plus a constant. Middle one is a power rule integral. Right, z to the negative 2 becomes negative z to the negative 1, or negative 1 over z. And then finally, ln abs x minus 1 minus 2 times 1 over x minus 1 minus ln abs x plus 1 plus c. All right. Where am I at for time here? We should be pretty close to out. Yeah, we're 4 minutes over. So we're going to take a little break, 10, 15 minutes, grab a snack. And then I will see you guys back here for lab. We're going to talk about the overall rule for PFD. So I'm going to give you a PFD Bible, kind of like the trig sub Bible, that will tell you, exactly what to do in what situations. There's one more nasty situation. We'll talk about how to handle that. And then we'll be done. So yeah, I'll see you guys back here in a few minutes.
Professor Foster,
Yes.
can I get a picture of the last page and this page at the top before you go ready?
Yeah, sure. So here's the top of this page.
All right, thank you.
And the previous page. Oh, sorry, wrong one. Oh, damn it. Here we go. Yeah, there's the partial fractions.
Okay, can I get the top of that? Oh wait, is that the top?
There's really nothing else here. Just the statement of the integral.
Okay, thank you.
Yep. Okay. Excuse my snack on the document camera here. I don't really have a better place for it. So I want to talk a little bit more about special cases in partial fractions, some kind of unpleasant things that can happen, a little bit things we can do to make our lives better. How we could do this a little faster. And then we'll be done. So let's do it. So what could be done to speed this process up? Well, from this line, so I'll give it a second. Is everybody back? A little confirmation. I guess I should make some noise and like tap dance or something so everybody can hear for a minute and tell it we're back and moving. I'm gonna get started on the lab here in just a second. First thing I want to address is what we could do to make this whole thing go faster. The answer is use a combination of that traditional method with the Heaviside method. So we're going to use Heaviside to get as much as possible at x equals 1, star becomes 4 times 1 equals a times 0 times 2 plus b times 2 plus c times 0 squared. So we get 4 equals 2b, which means that b had to be 2. And at x equals -1, star becomes 4 times -1 equals a times -2 times 0 plus b times 0 plus c times -2 squared. So this says that -4 is equal to 4c, which tells me that c has to be -1. So I've got b and I've got c. What I don't have is a. And there's no number I can plug into this equation that will make b and c go away without making a go away. The number you plug in to make c go away is 1. But if you plug in 1, the a goes away because of this factor. The number you plug in to make b go away is -1. But if you plug in -1, the a will also go away because of this factor. But nobody said everything needs to go away. You can take the information we got here and update the equation star. So that would become 4x equals a times x minus 1 times x plus 1 plus b, which is 2 times x plus 1 plus c, which is -1 times x minus 1 quantity squared. And then you can do all of your future work from here, right? So you could collect your coefficients from here and set them equal. You could plug in any other number you wanted. Let me show you just what would happen if we continued from here with the usual coefficients method. My x squareds would be a plus negative, I'll just write it out. This will be ax squared minus a plus 2x plus 2 minus x squared minus 2x plus 1. So you'd have 4x equals, where are my x squareds? I'd have ax squared minus 1x squared. That's a minus 1 x squared. My linear terms, I've got a plus 2 here and a plus 2 here. So I get plus 4x. And then my constant terms, I have a minus a, I have a plus 2, and I have a minus 1. So that is plus 2 minus 1. That's negative a plus 1. 1 minus a. And now, again, I do the 0. So a minus 1 equals 0. 4 equals 4. And 1 minus a equals 0. That's the system I get out of this, setting coefficients equal to each other on the left and the right. So instead of having to solve a 3 by 3, really any one of these top or bottom equations gives me the information I need. So the smart move here is on all of these partial fractions problems, after you've done your PFD setup and you've gotten to this equation star, use the Heaviside trick to get as much information out as you can. Get as many of those coefficients, right, A, B, and C, whatever, using the Heaviside cover-up method. Here I was able to get 2 of the 3. Then update that equation by plugging those values in, and then proceed with the normal method, right, the equating coefficients method, because that will lead to a smaller linear system, an easier thing to deal with. You may want to rewatch that procedure that we just ran through there, because it can be a little bit hard to reproduce if you haven't run through it just based on seeing it once. But I need to be efficient with time because I have a meeting today at 3. So I'm going to keep moving and show you 1 or 2 other little things. It's time for the PFD Bible. So this is the PFD Setup Bible. On the left, if the denominator has a factor of blah, 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 then the PFD setup must contain blah, blah, blah. All right. If the denominator has a factor like x minus r, a simple, non-repeated linear factor, then your PFD setup must contain a over x minus r, or some other coefficient. I'll use a, b, and c. If the denominator has a factor of x minus r raised to some multiplicity m, then your PFD setup must contain an escalating sequence of terms that builds up to whatever that multiplicity is. Right, like we saw in that last guy that had an x minus 1 squared, we had to have like a over x minus 1 plus b over x minus 1 squared. If that was a cube, we would have had 3 terms and so on. if your denominator has an irreducible quadratic factor, that is a quadratic factor that cannot be broken down over the real numbers, then your PFD setup must contain a linear term over that irreducible quadratic. And then if you're really fucked, then you have an irreducible repeated quadratic factor, in which case you need to have a tower of terms building up to the multiplicity, each one of which looks like this. So this is going to look like a1x plus b1 over ax squared plus bx plus c plus a2x plus b2 over ax squared plus bx plus c squared, building all the way up to amx plus bm over ax squared plus bx plus c to the m. This is your PFD Bible. This tells you how to write down the correct partial fractions setup for any proper rational function. I mentioned this en passant earlier. There's no such thing as an irreducible cubic. Thank God. There's no such thing as an irreducible quartic or quintic. Every polynomial of degree 3 or greater can be broken down into a combination of linear and quadratic factors. So this really does cover all the possibilities. I'm going to show you a nightmare example, and we are not going to solve it, but we are going to set it up. This nightmare example will contain all the scary things, and actually solving for the coefficients in this nightmare example would take hours to do by hand. Does everybody have this down? Does anybody need more time to write here? Okay, here we go. Scary example. Leave some space at the bottom of your PFD Bible. I'm going to come back and add a note there in a minute. Now here I've already factored the bottom, and good luck factoring that if I gave it to you multiplied out. X squared plus 1 is irreducible. But here it's not repeated. It's just an irreducible quadratic. X squared plus 2x plus 2 is also irreducible. You can compute b squared minus 4 times a times c. That's 4 minus 4 times 2 times 1 is negative 2. So this is also irreducible. How do you check, by the way, that ax squared plus bx plus c is irreducible. I said it there, but I haven't, you know. This is irreducible if and only if b squared minus 4ac is negative. The discriminant, right? If the discriminant is negative, then that quadratic doesn't have any real roots, i.e. is irreducible. Otherwise, the thing is reducible, can be factored over the real numbers because it has real roots. All right, so we've got two irreducible quadratics, one of which is repeated. We have a simple linear factor that is not repeated, and I have a repeated linear factor. So get ready. A over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. That is all from this factor, right? This is our tower building up to the multiplicity. Then from the x plus 1 factor, I'll have plus d over x plus 1. From the irreducible x squared plus 1, I will have ex plus f over x squared plus 1. Irreducible quadratic factors get linear numerators. The degree of the top has to be 1 less than the degree of the bottom, and we have to account for all possibilities. So above an irreducible quadratic, we have to allow for a linear function. And then we have our repeated irreducible. So that would be gx plus h over x squared plus 2x plus 2. And since he is repeated, we have to build up to his multiplicity. His multiplicity was 2. So this would then be ix plus j over x squared plus 2x plus 2 squared. That is the PFD setup for this function.
Will we ever have to solve something like that?
No. But
Thank goodness.
you need to know how to get any one of these pieces, right? I could take this together with this and ask you to do that. Or I could take just these together with this and ask you to do that. So being able to set up a big scary thing like this, as long as the bottom's already been factored for you, is a really good exercise to see if you understand PFD setups. There's almost always a question like this on my exam one. Nope, you can look in the book. They got shit like this. They got lots of things like this where they don't actually solve the whole problem, they just set up the PFD. And it's good practice, it really is. Okay. What else did I want to say? You guys remember from last time that I asked you to do the trig subintegral 1 over a squared plus x squared? And that's because stuff like this does show up a lot. Or not a lot, but it shows up from time to time. And that'll be arctangenty stuff. I'm gonna grab one of these problems. Let's see, am I forgetting anything? Yeah, there's the arctan thing. Let's do this, 2x squared minus x plus 4 over x cubed plus 4x. First, we need to check whether this is a proper rational function or not. And it is. The degree of the bottom is 3, which is strictly bigger than the degree of the top, which is 2.
Will they ever be the same?
Mm-hmm.
And what do we do then?
I'll show you in a minute. The space I asked you to leave down here is for that. But for now, one thing at a time. Factor the bottom. I can pull out an x. And I get this. So your first step is always to factor the bottom. Check if it's proper. If it's not, you'll do something else. I'll show you in a minute. If it is proper, factor the bottom, figure out your PFD setup. When you start the PFD, step away from the integral, right? So my next few lines, I'm not going to write any integration. Just algebra. So now I'm starting my PFD. I let my reader know. I say, okay, my function can be set up as a over x, simple linear factor, plus bx plus c over x squared plus 4. Because x squared plus 4 is an irreducible quadratic. You need to check that this shit is irreducible. If you don't know how to spot that right away, that's okay, but you need to check it. This is irreducible. The roots are plus and minus 2i. But you check by computing the discriminant. All right, so here's my PFD setup. Now I cross multiply to kill the denominators. And I get 2x squared minus x plus 4 equals. Here, when I multiply by x times x squared plus 4, the x's will cancel, and I will get a times x squared plus 4. And here, when I multiply by x times x squared plus 4, the x squareds plus 4s will cancel, and I'll get bx plus c. Don't forget to write it in parentheses. Fractions are grouping symbols. Times x, because the x squared plus 4s will cancel. This is the equation that you've noticed me calling star. If I want to be efficient about this, and I do, then I should use the Heaviside trick at this stage to recover as much information as I can. Then rewrite star with that information and proceed using the normal equating coefficients method. What value of x is useful to plug in here?
One.
So what do I mean by useful? I mean makes all but one term go away. If I plug in 1, this would be a times 5.
0.
B plus c. Yeah, so if I want to make all this shit here go away, I should plug in 0 for x. And technically what we're doing is we're taking a limit. We say as x goes to 0, star becomes two times 0 squared minus 0 plus 4 equals a times 0 squared plus 4 plus b times 0 plus c all times 0, which is the same as just saying 4 equals 4a. Because this shit's all 0 due to this 0. And if 4 is equal to 4a, then a is equal to 1. Unfortunately, the Heaviside trick won't get me anything else. So I should update my equation star with the information gleaned from Heaviside. Just close, sorry. And then proceed with the normal method. So now updating star, we get 2x squared minus x plus 4 equals 1 times x squared plus 4 plus, I'll write this out, this is bx squared plus cx. Which is the same as 2x squared minus x plus 4 equals x squared plus bx squared is 1 plus b times x squared. And then the only x I have here is plus cx. And the only constant I have here is plus 4. This I call 2 star usually. Oh shit, 2 star. From here, we can equate coefficients. Equating coefficients in 2 star gives me the linear system. Oh, don't use that, John. Gives me the linear system. Well, 2 and 1 plus b are both the coefficients of x squared. So 1 plus b has to be equal to 2. C and negative 1 are both the coefficients of x. So C has to be equal to negative 1. And 4 has to be equal to 4. That's not useful, but it is true, and it is something we get from equating coefficients in 2 star. So I'll write it down. Does everybody see where this system comes from? It's subtle, usually takes some time. But the coefficient of x squared on the left has to be equal to the coefficient of x squared on the right. The linear term on the left has to be equal to the linear term on the right. And the constant term on the left has to be equal to the constant term on the right. And this is a simple system, right? Right away, I can read off B and C. It's a nothing job. It would be much harder if I hadn't used Heaviside to pick up A at first. If I hadn't used Heaviside to pick up A at first, I would have had other terms in here. This wouldn't be such a sparse system. But from this, I can deduce that C is negative 1, of course, and that B is 2 minus 1, which is 1. So now I have A, B, and C, which means I'm ready to do the integral because now I know my PFD. I'll write A equals 1 here and box it just so I can copy it down and have it to fuck with. Here we are. Recall, this is the situation we were in. So now we are ready to rock and roll. Therefore, the integral of 2x squared minus x plus 4 over x times x squared plus 4 dx must be equal to integral of 1 over x plus b, which is 1x, plus c all over x squared plus 1 dx. And I can split this up. This is the integral of 1 over x dx.
Wasn't it x squared plus 4?
Oh, sorry, thank you. Yes. Plus integral of x minus, x minus 1 over x squared plus 4 dx. And in fact, the x minus 1 over x squared plus 4, sometimes these integrals will yield to u sub, kind of like that very first example we talked about, where the top was exactly the derivative of the bottom. But most of the time they won't. Most of the time you're going to need to split them up too. So this will be 1 over x dx plus integral x over x squared plus 4 dx minus integral 1 over x squared plus 4 dx. So here I just split up x minus 1 over x squared plus 4 using some simple algebra rules. This is x over x squared plus 4 minus 1 over x squared plus 4. So I get this. Now each one of these is relatively simple. Natural log, u sub, arctan. The arctan here, you're going to have to do via trigonometric substitution, unless you've proved the formula I asked you to prove last time. This piece is ln absolute value of x right away. This piece requires the substitution z equals x squared plus 4. It will be a natural log, but it's not super obvious. dz then is 2x dx. And over here, if you haven't proved that formula, then you need to substitute x equals 2 tangent theta. It's a trig sub, so dx would be 2 secant squared theta d theta. Or use the formula I asked you guys to prove. 1 over x squared plus a squared dx is always 1 over a times the inverse tangent of x over a plus c. You shouldn't use this formula until you've proven it, but it's not going to take you more than 10 minutes to prove, so you should prove it. This is what I mean when I say mathematicians are willing to work very hard to be lazy later. So you can either make this substitution every time you run into an integral like this, or you can prove the general formula and then just use it. If you prove it, you'll remember it. In any case, what we get here is the natural log of the absolute value of x plus 1/2 integral 1 over z dz minus 1/2 inverse tangent of x over 2. And I'll write my plus c here, why not? And then finally, this will be the natural log of abs x plus 1/2 natural log ab z minus 1/2 inverse tangent of x over 2 plus c, which is the natural log of abs x plus 1/2 natural log of x squared plus 4 minus 1/2 inverse tangent of x over 2 plus c. So this is how these integrals work. And you are almost in a place now where you can integrate any rational function. The only types of rational functions we can't integrate with this method are improper ones, where the degree of the top is not strictly less than the degree of the bottom. And that's the last thing I want to talk about here. Questions on these steps? Everybody's totally comfy?
I feel fine with this, at least.
So, back to this page. If you need to integrate an improper rational function something like integral of p of x over q of x dx, where the degree of p of x is greater than or equal to the degree of q. The first step must be long division. So you got to remember how to divide polynomials, which most people forget by the time they get to Calc 2, which is all right. That's what I'm here for. This will give you the output from such a division problem is a polynomial plus a proper rational function. And then, you know how to integrate polynomials, and then the proper rational function, you come back to all this good shit. So I gave you a couple of these in your homework. Let me see what sort of examples I have here. That isn't bad. Yeah, let's do this first. X cubed plus x over x minus 1. So I'll hold here for a second. Anybody needs right? Okay. Here we go. Killing again. X cubed plus x over x minus 1. I recognize that this is a rational function, but it's not proper. That means we need to divide. If you look in, if you look in your modules, this is special just for you guys. I have several things on polynomial division, right? There's a video here, Patrick JMT videos, all of this good stuff to help you get comfy with dividing polynomials just for this portion of the class. The trick is just like dividing numbers. I like to write in any of the missing terms, and I recommend you do the same. And then you set it up just like you set up long division in second grade. Here's the thing I'm dividing. Here's the thing I'm dividing by. The trick to dividing polynomials is to pay attention just to the lead terms. I don't give a shit about this, and I don't give a shit about this one. I ask, by what must I multiply x in order to get x cubed? And the answer is?
X squared.
Yeah. So I write that up here. Then I take this and I distribute it over these two terms. So x squared times x is x cubed. X squared times -1 is negative x squared. So I write down here x cubed minus x squared. And then I subtract one whole row from the other whole row. X cubed minus x cubed is 0. X is 0x squared minus negative x squared is positive x squared. And then this x, I'm not subtracting any x's, so he will come along for the ride. And you can write the plus 0 if you want. So I just take this row and I subtract this row from it. This is the result. Very similar to long division for numbers, if you remember that. Plenty of people don't, it's okay if you don't. Again, we just pay attention to the, so that's one loop, right? Like think of this as an algorithm that runs in loops, that's one loop. Now you just do it again, starting with this. By what must I multiply this to turn it into this? Lead terms only. By what must I multiply x to turn it into x squared?
X.
Yeah, just x. So I write up here plus x. If it was a negative x that I needed to multiply by, I would write minus x. All right, plus x, and now I multiply this term by these two terms. So x times x is x squared. X times -1 is minus x, and then I subtract one whole row from the other. X squared minus x squared is 0. X minus negative x is 2x. And that's one more loop. So now I start again. By what must I multiply x in order to get 2x? It's 2. Then I distribute the 2. So I'll have 2x minus 2. Subtract, you can write the plus 0 here if you want. Subtract one row from the next. And I end up with 2x minus 2x, that's 0. 0 minus -2 is positive 2. This guy is called the remainder. This is called the quotient. And the result is that when you divide one polynomial by another, you get the quotient plus the remainder over the divisor. So what we learn here is that, I come down a little further, x cubed plus x divided by x minus 1 is really equal to this quadratic polynomial, x squared plus x plus 2, plus this remainder over this divisor. So like I said, you get a polynomial plus a proper rational function. And now if I want to integrate the object on the left, it suffices to integrate the objects on the right, because they're equal. So the integral of x cubed plus x over x minus 1 dx is equal to the integral of x squared plus x plus 2 over x minus 1 dx. If this was a more complicated rational function, then I might have to still run some PFD on this, right? Sometimes after doing the long division, you just end up with something here that requires PFD. We got lucky here. This is a little u sub thing. So this is x cubed over 3 plus x squared over 2 plus 2x plus 2 times the integral of 1 over x minus 1 dx, in which we make the substitution, z equals x minus 1. That's okay. And now dz is dx in this integral. So I get x cubed over 3 plus x squared over 2 plus 2x plus 2 times the integral 1 over z dz. And that's going to be a natural log. This is x cubed over 3 plus x squared over 2 plus 2x plus 2 times the natural log of the absolute value of z. If it's okay with you, I'm just going to go ahead and write the x minus 1 plus c, and that is your answer. Okay. You guys now know as much as anybody else on the planet knows about integrating rational functions. This is one of those very few, very rare areas of mathematics where we can say it's all done. We know all of it. Integration of rational functions is totally solved by long division, partial fractions, u sub, and trig sub. Trig sub only in the nastiest cases, those like arctan things.
Are we gonna have these problems, but definite integrals?
Yep, absolutely. So the way you handle these as a definite integral is the way you handle any other definite integral. You find an antiderivative and evaluate between bounds. If you end up splitting it into pieces where you need to make a substitution, you should change the bounds in those substitutions. But yes, certainly. I have a few minutes left here. Now, like I said, I got a meeting at 3, so I got to run right at 3 o'clock. But I can spend 5 more minutes solving any problem you guys want to solve. Is there anything from the homework or study guide that you desperately want to see, driving you crazy?
I think I have one.
Yeah, what you got?
Was it homework? It was homework for question 6.
Do you have the problem handy by chance?
Yeah.
Yeah, please. Go ahead.
Give me 1 second.
I'll see if this will let me in fast. But it takes a minute usually. So.
Homework for question 6. I had integral 3t sine squared t dt.
All right. By parts, right? I've got a polynomial times a trig function here. The inside of the trig function doesn't have this as its derivative, so u sub won't work. So this is by parts. Following LIPET, I pick u to be my polynomial, which is 3t, and dv to be everything else, which is sine squared t dt. du is 3 dt, and v here is going to require a little bit of love. To integrate sine squared, I call it 1/2 1 minus cos 2t dt. So v is the integral of that, which is 1/2 t minus sine 2t over 2. So that's my IBP table. And now I follow the formula, u times v minus the integral of v du. This could, of course, be written more nicely if you wanted to. I'm going to be impatient here. I've got a 1/2 and a 3 that can come out of the integral. And then I've got integral of t minus sine 2t over 2 I'll write as 1/2 sine 2t dt. So this is 3t over 2 times t minus, I'll write this that way too, 1/2 sine 2t just looks nicer, minus 3/2. Now in here I can integrate each of these pieces pretty nicely. T is going to integrate to t squared over 2. And then I'll have minus 1/2 times sine 2t integrates to, let's see, is that negative cos? It is, yeah. So that'll change this to a plus cos 2t over 2, close this, slap on a plus c. And then we should clean up a little bit. This is going to be 3/2 t squared minus 3/4 t sine 2t minus 3/4 t squared. And then distributing this, we'll have minus, I've got 2 times 2 times 2, this is 3/8 cos 2t plus c. So it's an IBP, but the dv to v step is a little bit tricky, right? Just to go from dv to v requires one of those 7.2 trig integrals because you have to integrate sine squared. So if this one's giving you a hard time, I would come back to this. It's IBP with u equal to 3t and dv equal to sine squared of t dt. To get
I think my mistake was that I took out the 3 from the first start and then I did u equals t and du equals dt.
So
Would that still work anyways?
it's okay. Yeah, popping the 3 out is fine. But when you set up your IBP, it has to be, you choose u and you choose dv. So if you wanted to pop the 3 out at the start, that would be fine. U would then be t and dv would still be sine squared of t dt. So I would
Yeah,
try.
my answer looks very similar.
Yeah, if you want, send me a picture of your work. I'd be happy to take a look and see if there's anything I can do to help you out with it. Probably there's a little mistake in there somewhere if it didn't come out right. But I got to get running, guys. Unfortunately, I got this meeting to move to. So if you want to talk about any other problems, anything like that, please don't hesitate to ask for help. Send me a Canvas message, send me an email. We can schedule extra office hours, or you can just send me a picture of your work and I can give you feedback based on that. The study guide is out. I dropped the study guide yesterday. So you can start working on that in WebAssign. Remember, to get credit for the study guide, you need to submit the scans of your work for those problems to Canvas. That's where the study guide grade comes from. And you want to do that as soon as you can. That way I can give you some feedback on your work, and we can prepare you better for the tests that way, because you'll be able to see how I grade. All right, you guys are awesome. Thank you so much for hanging in here. I know these Thursdays are long. You're all doing great. Please continue working hard. Remember, the test is 1 week from today. So work on that study guide, work on that homework, and do not hesitate to ask for help with anything you need help on. I am here to help. The tutors in the Learning Commons are available through Zoom, just like me. They can help too. They're pretty good. If there's anything I can do, like I said, just reach out and I will work with you as much as possible. I will see you guys on Tuesday.
Office hour
Alright.
tomorrow, same time?
Thank you.
Yep.
All right.
All
thank you.
right.
Have a
See you
good one.
tomorrow, Professor. I'll see you during office hours because Lord knows I need a little more help. But have
That
a great
sounds
day.
good. Yeah, I look forward to it. Take care, guys.